All right, so I did get a question asking about stability of the enols enolates with regard to aldehydes versus ketones. So one good way to look at this is, let's say that we have an enol. We're going to produce an enolate ion, so we're going to extract a hydrogen. And what happens with the enol polymerization is that when we extract that hydrogen, we end up creating a carbanion. And this carbanion is resonance stabilized, so this can go back and forth like this. And same thing here, when we extract this hydrogen, we create the carbanion, we can get a structure that looks like this. So in terms of why one would be more stable than the other, tautomerization kind of falls under this gray area that it is and isn't resonance. So in this case, we're going to treat it like it's resonance. And so these two hydrogens here, this hydrogen can actually bump back and forth. We can lose a hydrogen off of either one. So in this case, we end up with two stable configurations and two ways to generate the enol enolate ion, whereas with an aldehyde, we only have one. So this is kind of the hand-wavy explanation as to why ketones are better. Now, there's also kind of a lot buried here within the molecular orbital theory, which isn't a better theory. Well, let me say that. It's a more complete theory than Lewis theory that explains why when you do a carbon-carbon bond in these molecules, they end up being a lot better at handling these type of charge stabilizations than a carbon-hydrogen bond. But if you're looking for kind of like, again, that hand-wavy Lewis theory explanation, we have more tautomerization options with a ketone than we do with an aldehyde. And because we have more tautomerization options, more different configurations to distribute the high energy of generating that enol enolate ion, and so it's more stable. And that was kind of the only question I got. So this was in regard to the discussion board for Organic 2, where you're going to do the aldol condensation and aldol addition reactions. Again, for that reaction, you're given this ketone, diethyl ketone or 3-pentanone. That's going to be what forms the enolate ion, and that's going to be what attacks the aldehyde. So you're going to end up with 3 aldol addition products, and then those are going to condense to give you the aldol condensation products. You need to name those on the discussion board. So I did this yesterday. If anybody asks, I'm going to do it again. But they're lengthy names. We're going to skip the cis trans RS that you would get, the RS you would get for the alcohol, the cis trans you would get for the condensate. You're going to get mostly trans for the condensate just because that's more stable. There's few examples of cis isomers being more stable. That said, you're still going to get some cis isomers. When it comes to the alcohol, because the aldehyde is trigonoplanar, you're going to get both the R and the S configurations. So I thought it was just way too much to ask you to name, like, okay, do the RS for each, and then do the cis trans for each. You're welcome, Lauren. Yeah, I'm sorry this is kind of a hand-wavy explanation. There's probably a better answer with molecular orbital theory, but that's the way I understand it. More tautomerization options, and tautomerization is like resonance. The more resonance options you have, the more stable. The more tautomerization options you have, the more stable. Okay, so the reacts with the acids. So when you do the azide lab or the azo dye synthesis lab, you start with aniline, and we're adding the HCl first just because it's convenient. It's also a highly exothermic reaction, so we can add the HCl independent of the sodium nitrite and kind of make sure that this reaction doesn't get too hot and drive a lot of side reactions. So when you first add that HCl, you actually form the amine salt. And so if you get a thick viscous liquid, this is what I was referring to, is that it's pretty rich with this salt. So what happens next with the nitrite is actually two reactions. So first, we're going to form the nitrous acid. And then you can look it up in the notes. It's not essential to know this mechanism, but this HCl, this nitrous acid, will actually convert this into this ion here, the N2 plus diazonium salt. This diazonium salt loves to attack benzene rings. And I think it's a plus. I'm trying to remember off the top of my head. It may be a negative. Probably a plus. So if we have any benzene ring with an R group, honestly, it does not matter what the R group is, because this diazonium salt is really, really big. And because it's really, really big, it's always going to do the para position. So you've got ortho, meta, para. And I always remember it as ROMP, ROMP, your R group, ortho, meta, para. It's always going to add to the para position. And the big reason for this is purely steric. It is way too big to ever try the ortho position. And even the meta position, you're kind of pushing it. So we're always going to end up with something that looks like that. Specifically if we're starting with aniline as our starting amine salt. Yeah. All right. Glad I got you, Lauren. Orgo 1, test 4, homework question 54. I feel like I can draw the structure on paper, but not digitally. All right. So let me bring it up. Almost there. You have the structural formula for the carbocation amide that leads to the major product in the reaction of hydrogen chloride with cis-2-butene. So when we do the HCl, if we're going to go through the carbocation route, we're going to get attack on the hydrogen, and this will give us this structure here. So let me show you on my desktop, and we'll see. It's just a matter of just the drawing. I would assume that was pretty easy to get to. Now to fight with the drawing system. Yep. That would be my guess. Is this you probably have it correct? It's just more the nuance with it. But yeah, just draw butane and then put a carbocation on the second carbon. But I 100% agree with you. I think you understand how to do it. Knowing you, I'm pretty sure you know how to do it. I'm pretty sure it's just a matter of like formatting it. Which is part of the reason why I make the homework waver so little is that it's a formatting issue. And particularly with Chem 1, Chem 2, I tell students, like, if you're struggling, send me an email because on my end, I can see what the right answer is and I can see what you put. And I can tell you if you're a complete left field or if it's an issue of formatting. And particularly because Chem 1, Chem 2 are taught with WebAssign, most times I'll tell students, you got it right. This is what you need to enter into the problem. Cool. Glad it worked out. Good for it, girl. You got it. One more. There's so upset when I set that stuff up so you couldn't be destructive. Question 65, part 4. I think it's K potassium hydroxide, but I don't understand why the other one doesn't work. Let me bring it up. Question 65. Question 65. Design a synthesis of 2-methyl-2-pentanol from 1-bromo methylpentane. Choose the best option for the immediate precursor to the target molecule. Based on the options they give you, it's definitely going to be, I guess I can share. So you're trying to make this molecule. Well, I guess I can show you on the desktop. So in terms of desktop, right now, you're making this. The only choices that really kind of make sense would be, well, you're starting with this compound on the right, and yes, this drives me up the wall that the reactant is on the right and the product is on the left. But they're asking what would be a good intermediate, so easiest here to do is an elimination, and the elimination would give you C. And then the best precursor to making that would definitely be your starting reagent. So a nice two-step synthesis. So the next part asks you, like, what's a good way to run this reaction? Yes, I want to move forward. Why would you put return to question halfway up the page? So how would you do it? Well, you've got potassium, so we can go through the ones that do and don't work. Going from this to this, HBr won't do anything. It mostly be a substitution. Sulfuric acid, you can do this, just acid catalyzed dehydrations of alkyl halides. Pretty hard to do, and on top of that, these prefer an SN2 mechanism or an E2 mechanism. This is going to more drive an E1 mechanism with water. So yeah, that C and E are more if you're trying to dehydrate alcohol, so this leaves you with A and D. A is the preferred choice. D will do some eliminations, but what we consider this is a small base. So this eth oxide here, do the check my work to make sure what I'm telling you is correct. The reason why we wouldn't want to work with eth oxide versus tert butoxide, it's pure sterics. So we've got eth oxide, and we've got tert butoxide. And this is something I feel your book doesn't really do a good job of explaining. But there are two things that these can do, because these are nucleophiles. And one option you're probably looking at here is elimination. They can both attack this hydrogen, and we knock the bromine off and we get the alkene. The other reaction they can participate in is the SN2 mechanism. So they can actually displace the bromine. And in this case, we will actually get a small amount of ether out of this reaction. This is actually a variant of the Williamson ether synthesis. So we'll talk about this at the end of the semester. This is totally possible to do. What we want to do is create a base that is so big, it really doesn't want to undergo SN2 substitution. So this will do some elimination. It's more inclined than the tert butoxide to do the substitution because it's so small. It can actually fit in there and push the bromine out. The tert butoxide is far more likely to do the elimination just because it's so big it can't really get in there and knock the bromine out. But that said, if your intuition is to say, well, can't they both do substitution? Yes, and you will get a small amount of ether regardless of which one of these you use. It's just the tert butoxide is far more likely to give you what you want. And then the last part of that, what's a good way to convert that alkene to good way to convert that alkene into an alcohol based off the options they give you. HCl is going to give you a halide. Water will do something, but not much. We typically do a water catalyzed, an acid catalyzed addition. E, elimination. This borohydride is actually going to give you the alcohol as a primary alcohol. So your only option here is C. Makes any sense? we expecting to do the theoretical percent yields for the ASO lab since we just covered the mass? No. I pitched that the last minute. I've had a lot of instructors that they're like, when they do organic chemistry, like, oh, they need to be calculating yields. They need to be calculating yields. And I understand that. Like, there is merit to calculating yields. I don't see a merit to calculating the yields with the azo dyes. There are two reasons for this. One, we simply just did not have time to dry those materials. Maybe if you came back the following week and dried them, but that would be a pretty pointless thing to return to the lab for. The second is that we are running very small amounts of these materials, and so particularly a lot of you, when you ran this reaction, you noticed there was like this brown oil that sat on the top. That's your unreacted aniline. So unless you really do the synthesis really well, like you're really controlling the proportions, which we really can't do because of how small we're working with, and you do a really good job of crashing out the azo dye, which depends on the dye, you're going to have pretty nasty, pretty all over the place yields because you can't really drive this reaction to completion. So the point of this lab is, not make an azo dye and characterize it in terms of like the yield. The point of this lab was to see the effect of substitution groups, adding groups to the benzene rings on the azo dye. So long story short, we're not going to worry about percent yields because that's not really the focus of this lab. You couldn't dry the materials in time. I don't care about the percent yields. What I do care about is that you do see the effect of changing the groups on those benzene rings and the effect it has on the color of the dye as well as the absorbed wavelengths. Yeah, you're welcome, Niall. I had a lab manual in grad school that like you could actually see through the first 10 pages because I burned a hole through it with sulfuric acid. It's always a good sign for your lab notebook if it's just covered in like dyes, acid burns, and things like that. I always got paranoid of the graduate students and scientists are like, oh, look at my really pristine lab manual. I was like, no, 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 no. It needs to be completely trashed. Like, it needs to be wet because you spilled something on it because it was right there while you were doing all the work. Anytime I see a pristine lab note, it was like, yeah, that was on the other side of the room the whole time. You were clearly not writing things down as you were going along. All right, thanks. And yeah, glad we had those spec guides for the lab. enjoy your weekend too, Lauren. We'll see you next week. Next week for Orgo 2, y'all are making soap. I don't think it's a particularly interesting lab, but you're doing the practical the week after that. Practical is a rite of passage lab. Everyone who takes organic chemistry should make aspirin. You're going to be making aspirin. It's going to be a little underwhelming because we break into 2 weeks, but honestly, it's kind of cool. I still have the aspirin from when I made it in organic chemistry. Question 71, how to start it. Suggest a reasonable mechanism for the following reaction. Well, on the upside, they do kind of like spell it out a little explicitly in the start. So the first start, it's like any acid. You're going to get an attack on the hydrogen to break your hydrogen-oxygen bond. So I'll show you here on the screen. So our double bond is going to attack the hydrogen. We're going to break that bond. And our organic structure is the cyclohexane with the carbocation. And the inorganic, man, they're going to make you really draw this. Okay, let's do this thing. Just saying, this kind of feels like busy work. It's so kind of funny to see how they're drawing this. Like, organic chemists are like hardcore about like the octet rule. This is one of those exceptions. I'm sorry, I just think that's kind of funny. All right, so there's your first one. And then the next mechanism, pretty straightforward, is the iodine is going to attack carbocation. There it is. So yeah, the first part, you're just abstracting a hydrogen from the phosphoric acid, and other than it just being tedious, that's going to end up being your final products. Yeah. Um, yeah, it's just more the wording of the problem. Question 73. I can't seem to draw the three-member ring made by the bromine and two carbons. So if you're having issues with matching the structures in the soft shock, don't worry about it. There's a couple, I think there's two that are flipped. So when I've been grading the assignments, I've just been giving back the points for that one. But Rachel actually pointed out like a couple of them don't match up. So what I need to do, I can't change that aspect of the module without completely reloading the module. And to completely reload the module means that all your submissions are gone. So you'd all have to redo it. So we're just going to say for that question, if you're getting it wrong, you can ask me in person, but don't worry about it. You probably did it right. Three-member ring. All right. So let's see how it's going to play. So if I remember correctly from last semester, this is a real pain to draw. Okay, just making sure I got it up. So for this one, blame it. Easiest thing to do is to draw the two groups going back. Oh, how does this work? Actually, no. So you're going to draw, I think, these in plane. You don't need to worry about the hydrogens. Actually, you do. Okay. So the hydrogens, I think the easiest thing to do is to push them back. And then make the bromines wedges. And they need to be fatter at the top. And also don't forget that the bromine here should be a carbocation, or should be a cation. Not a carbocation. Oh, and then I need to draw the mechanisms. Sorry. And this is some nightmare how you draw this stupid thing. Okay. So yeah, you're going to draw it. Easiest way to do it, apparently it thinks the easiest way to do it is put everything in plane and put the bromines with the fat part up, and then make sure you put the cation on top. And then the rest of this should be pretty self-explanatory. But I do remember previous semesters having issues like it's kind of picky with the stereochemistry. Yeah, you're welcome. Hmm. Oh, there we go. You done being destructive? At least with your toddler's understanding of being destructive. All right, so it looks like we're kind of finishing up today. Again, if you ever have questions before the live streams, you can email them in advance if you're not able to make live streams. Otherwise, I will see y'all next week. Well, go, Bratosaurus. Go take your nap.